Just want to do it in a browser.
Okay.
Yeah, you can start on your.
Okay. Okay. Hello, everyone. Today we are going to talk about CNN architectures. And my name is Ma Yunshan, and I am a first-year PhD student. Let's get started. Sorry for everyone with us. Last time, maybe we talk about deep learning frameworks like Capital, PyTorch, TensorFlow, and most of the frameworks are developed and maintained by big company, internet company, and software company. And maybe you have noticed the news several days before that Yusha Benjo announced that Cyano is stopped maintenance and development about September 29. September 29. Yeah, just news several days before. So I think we better use the platform maintained by big company. It will much convenient because it have a continuous maintenance. Yeah, and such deep learning frameworks have so many advantages. First, it is easily to build big computational graphs, and second, it will be easily compute gradient, and then it will much more efficiently on GPU. Yeah, and each layer it is designed modularized layers, which will have forward and backward paths, and we can define the layers as a sequence, which is very intuitive. And today we're going to talk about CNN architectures. First, we will talk about several main structures in a chronological sequence, which is AlexNet, VGGNet, and GoogleNet, ResNet. And then we're going to talk about several brief talk about several other networks. First, let's begin to have a review about the LearnNet file. LearnNet is named by the creator Yang LeCun at 1998, and it is the first time CNN used to do image recognition, but the data set is not so large. It is a simple implementation, which only have 2 convolutional layers and 3 fully connected layers. So this is why the architecture name is LearnNet 5. As we can see, the green layers are the convolutional layers, and the orange is the pooling layer after the convolutional layers, and the last 3 layers are the fully connected layers. Yeah, this is the first time CNN was used to do image recognition. Yeah, and in 2000 and 2012, AlexNet was the first time CNN architecture was used for large-scale image recognition. The dataset is much bigger than the LearnNet used. The LearnNet used the dataset is the MNIST dataset, about it's total about 60,000 pictures, but AlexNet dataset is about 1 million, over 1 million. Yeah. This is the architecture of AlexNet, just much deeper than LearnNet. And it first have a convolutional layer, max pooling layer, and a normalization layer, and then repeat the first part, followed by 3 convolutional layer, and then 1 max pooling layer. The last 3 layers are fully connected layers, This is the whole architecture of AlexNet. And let's get started. The first layer. The first layer is the convolutional layer. The convolutional filter is 11 by 11, and depth is 3 because the image has a depth of 3 channels. And the filter numbers is 96 applied at stride 4. So there's a question, what is the output volume size? It means the convolutional filter applied to the input image, and then the output volume can be computed as this formation. It is the size of the input image minus the size of the filter over stride and plus 1. So the output of the first convolution layer is 55. And then
the dimension of the width or the height, right?
Yeah. Yeah.
But we still have many filters being applied, like 96.
Yeah, 96 filters, and each filter will generate one channel of the next layer. Yeah. And what is the total number of parameters in this convolutional layer? Actually, the parameter is the numbers in the filters. For each filter, its width and height is 11 by 11, and depth is 3. So each filter will have 11 times 11 times 3 parameters, and we apply 96 filters for the input layer. So the total number is this 35K. And next, followed by the convolutional layer is a max pooling layer. Yeah, it applies 3 by 3 filters at stride 2. The output volume size, the computation method is the same with convolutional layer. Just the width and height minus the size of the filter over the stride plus 1. So the output of the first pooling layer is 27 by 27 by 96. Yeah. So what is the number of parameters in this pooling layer? Yeah, because as we talked about before, the convolutional layer's parameter is the numbers in the filters, but the pooling layer we just do sampling in the output of the convolution layer. So there is no parameter in pooling layer. Yeah. So we just show the first convolutional layer and the first pooling layer. Here is a whole view of all the layers, because AlexNet is not so deep as the following CNN architectures like ResNet and so on. It only have 5 convolutional layers and 3 fully connected layers. Total number of layers is only 8. So all the settings and parameters of these layers can be shown as here. Yeah. As we can see, the first convolutional layer without padding, but the following convolutional layer have different padding size. Yeah. And there are some other details on the retrospectives of the implementation. We're just briefly talking about the convolutional and the pooling layers setting, and there are some things we can notate. We should note. First is that in AlexNet, they first use ReLU activation function. This is first time ReLU used in neural network, both as the activation function after convolutional layer, each convolutional layer, and as the fully connected layer. And the second, they use norm layers, after each polling layer, just to reduce the overfitting, which is very common use in nowadays neural network. And third one is it uses heavy data augmentation. The data augmentation methods used by AlexNet mainly from two ways. First is to crop, shift, and rotate the pictures to generate much more training sample. And the second one is to generating the density of the RGB channel of the input image, which you can see as the AlexNet paper. And it also uses dropout in the fully connected layers, and the batch size is 128. It uses the optimizer is SGD momentum. The parameter is 0.9, and learning rate is 0.01, reduced by 10 manually. When in validation site, the accuracy reached the plateaus. It means when the accuracy in validation site didn't decrease, then it will automatically reduce the learning rate by 10 times. And there are two, the last one. They also use 7 CNN output ensemble, and the accuracy have a significant improvement. It just maybe do average of the output of seven different training. And some more details is that, as we can see, the first convolutional layer in the figure shows that it isn't 96. Depth it isn't 96. It's only half of that, 48. That is because it is a historical reason. Because in 2012, they only used the GTX 580 GPU. It only has 3 gigabytes of memory. They cannot fill all the neurons and the parameters in one GPU. So they implement the same architecture on 2 GPUs, and each so they divide all the channels to two different GPUs. And for the convolutional layer 1, 2, 4, and 5, they are implemented on 2 GPUs, and the parameter didn't share with each other. And for the convolutional 3 and the last fully connected layers, they are implemented. There are connections between the 2 GPUs, and they will have parameters sharing. So here is the performance of AlexNet. Because AlexNet is the first CNN-based winner for ImageNet competition. It has a significant improvement. It only have 8 layers. And in the next year, 2013, it come out the FNet. It just improved the hyperparameters. All the network structure is the same. It's only different filter size, different fully connected size. Yeah. Performance still improved. Here is a brief introduction of the FNet, but the figure is some error. We just say two tips. First is it only changed the filter size. Yeah, the first convolutional layer changed from 11 by 11 strat 4 to 7 by 7 strat 2, and the convolutional layer 3, 4, and 5 they use different filter size. Yeah. So this is the FNet. It only changed some hyperparameters, and the network architecture is the same with XNet.
Is there any motivation or rationale behind this change?
Maybe I don't know what the motivation.
Described in the paper in the Sealer and Fergus 2013.
You mean the FNet?
Huh?
You mean the change from XNet to the FNet? Is there any reason?
Yeah, so you're saying that the main change was change in the hyperparameters, which is the strides 11 cross 11, 4 strides was changed to 7 cross 7 stride 2, right?
Yeah.
Okay. So did this brought down the error, right?
You mean this promise improvement?
Yeah.
Yes.
Yeah. So why?
Yeah, from?
Why?
Why?
But I think the second one is also important. It widened the networks.
Okay, cool.
I think in there's a paper after ResNet called Wide Residual Network.
Right.
They have some study that says that regardless of the network, if you increase the width, it almost always improves accuracy.
By width, you mean that the width of
The
the layer?
number of feature maps. Yeah.
Yeah.
No, width. The filters are increased from 3 or 4
filter
to 5.
size. You are increasing the filter size, but then the filter size is actually decreasing from 11 cross 7 to 7 cross 7.
No, they
So
increase.
talking about layers 3, 4, and 5, right? You're saying the second set of changes, right?
Okay.
Yeah.
So instead of using 384 in depth, right? That's the number of filters. It's not width, right?
It's width. I mean, the depth is how many layers you have.
Okay.
Yeah.
That's not what it is.
Number of filters is basically more combinations. Like for example, something comparable to NLP would be you are using a bigram model, now you are using a trigram and 4-gram model, something like that.
Not really.
It's
So, but okay.
7 by 7, 512 stacked on top of each other, right?
So I looked at the diagram and I think of each layer having a volume. That's what we were calculating before, right? The volume is the output of the filter convolved with the image, right? So you have like 11 by 11 stride 4, right? And that gives you the resulting height and width of the output, but then you need a depth for the number of filters you're applying, right? So that's why when you said 384 to 512, I was thinking that's the depth. If you look at the graphics, you can see those diagonal arrows. Those are indicating the depth.
Yeah, but the
number of filters.
Yeah, but the terminology is they refer to the number of channels as width and the number of layers as depth.
Okay.
So yeah.
So I can't seem to see the number of filters wouldn't be. I can't accept that is depth. Why is it depth?
I mean you're giving a volume, so it should be height times width times depth, right?
Okay.
I mean it is depth. I mean it's like a channel, but the thing is when you're referring to the whole network, then the depth is actually the number of layers. Yeah. The width is how many channels inside. I mean how many channels in your feature maps, which is actually depth, but it's called width. when you're referring to the whole network architecture.
Okay.
Yeah. So I think they don't explain why the width improves performance, but it has been observed that increasing the width generally improves performance. Yeah.
I mean, I see the intuition. So in an equivalent in an NLP would be, so if you have a feature maps for just bigrams, and then you increase it to like feature maps for 4 grams, you're increasing the receptor size, right?
No, I
No,
don't think
that's not the same?
accurate.
Okay.
I
I
think
think that would be same as this one, I think, the 11x7x7. Okay.
yes,
Yeah.
yes, yes,
Right.
yes.
When you're increasing the number of filters, you're basically admitting the possibility that there are more different types of features,
Correct.
different
Yeah.
textures,
Yeah.
or different
I understand.
edges
Yeah,
that
exactly.
you're trying to capture.
And in fact, this aspect is not only observed in CNN. I mean, in my other class, the neural class, it also applying to fully connected layers. So, but the side effect of this is if you increase the width, it is also becomes much easier to overfit to the data. So you will need stronger regularization to counter the effect.
Okay.
Okay, so the question still remains, like, there are 2 different changes here. One is, for the first layer, change the resolution down to 7x7, but admit more output, right? Because you're going at stride 2 instead of stride 4, right? And the second change is that you change the upper layers of the convolution layers to a larger width, right? Basically having more filters. Right, so the second one admits more higher level features, and the bottom one admits higher resolution, right? Because you're going at stride 2 instead of 4.
Yes. I guess the first one preserve finer level details.
Mm-hmm.
I mean, it can be thought of as preserving more finer level details.
Mm-hmm.
What preserves finer details?
The
By
complement.
Okay. Yeah.
Yeah.
So you are making it smaller and moving slowly.
So that when
yes,
you look at the final
that makes
results,
sense.
there are more pixels retained at the
Right. Okay, so all in all, you're just still trying to model more at a fine grained level from the input data, right? That's the effect of both the change.
I imagine so, but
Yeah.
I'm not sure what percentage. I mean, in terms of contribution.
Does this?
Yeah.
It's more like hyperparameter tuning.
Yeah.
Yeah.
But it makes some sense, yeah. But yeah, I'm more satisfied with this explanation.
Mhm.
But they don't provide any explanation in the paper, right?
I don't know. I haven't read the paper.
Maybe
Yeah.
you guys are welcome to look now and then post it on Slack.
Okay, let's continue. Yeah, and after that, in 2014, the neural network layers become much deeper, and the performance continue improving, like VGGNet and Google Net. So next part will introduce VGGNet and Google Net. Let's welcome another teammate for the following part.
Yeah. So, hi. My name is Sriram, and I'm coming from Yokogawa Engineering Asia. So previously we saw. Previously we saw these shallow networks, which have these 8 layers, and for the ImageNet large-scale visual recognition challenge in 2015, if I'm not wrong, or 14. Yeah. So in 2014, there were 2 networks which performed very close, and one was Google Net, which was the winner, and the other was VGGNet. And in terms of depth, again call these deeper networks, and they had similar layers like 22 and 19. So they were like similar in the depth and performance as well. So okay, so one of the main changes from the previous one to VGG was they had smaller filters and deeper networks. In the sense, instead of having multiple hyperparameters for choosing the number of filter size and the depth and so on, they just fixed on using only 3x3 convolution with stride 1 and padding 1, and 2x2 max pooling with stride 2. So they kind of fixed on these parameters, and they'll just stack these smaller filters on top of each other in that sense to get a deeper network. And it got a error percentage of 7.3 in comparison to 11.5 of 2013, which was the ZFnet. So and also they what they did was they tried out different architectures, and kind of the 16 and 19 layers performed well. And also for the 16 and 19, they are like similar in performance, but with 19 is just additional layers and more parameters, but it's just a slight improvement in performance. So the question is, why do you use smaller 3x3 filters? So over here, effectively, by using 3x3 con filters, it's basically giving the same receptor layer as a 7x7 con filter in the previous ZFnet. In the sense, if you look at this, say for example, you have a 224x224 image, and write it down. So say for example, you have a 224x224 image, and so you have 3x3 filters, right? So the first con layer is going to change it to so that's like 222, and the next one is 220, and the next one will probably be 218 cross 218. This is without any zero padding, and effectively this is same as putting a 7x7 con layer. So you put a 7x7 con layer and without any zero padding, and it's going to give you the same thing after three smaller convolution 3x3 layers. So it's basically the same thing, but one advantage is now it has so basically a stack of 3x3 con layer has the same receptive field as a 7x7 con layer, and now it's just more deeper, and you're introducing more non-linearities after each layer, and you are computing lesser parameters. So that's good. So moving on. So this is the whole architecture, and if you see, you have a bunch of convolutional layers, and then a max pooling, convolution max pooling, and so on. So you just stack this up, and then after that you introduce fully connected layers. So you have 2 fully connected layers with of dimension 4096, and then 1000 dimension fully connected layer just before the softmax to do the classification. So here they're just talking about the overall memory and the parameters which are being computed at each layer, and yeah. So and at one forward pass, you can see that the total memory. I mean, just summing up all these memory, and you see that the total memory is about 24 million, and each number is of 4 bytes. So that's like 96 MB per image. That's only for the forward pass. And then when you're doing the back prop, that's like 200 MB per image. So that's quite computationally complex. And for the total parameters, it's like computing 138 million parameters for the whole network. So one interesting thing over here is, if you see on the top layer of the VGG network is the most memory intensive part of the network. In the sense, if you look at the initial con layers, that's like 3.2 million numbers right there. But in terms of the filter size, it's smaller, so the parameters are less. So, but as you propagate through the network, you can see that probably around this pooling layer, the image becomes very less. It's like 7x7, but the depth is like 512. So it's like a smaller image with a very deep network. But then the parameters of the fully connected layers are actually a lot. So it's like 7x7x512 times 4096 of the fully connected layer. So the bottom layers of the end layers of the architecture has lower memory, but a lot of parameters are being computed at that place. So that's and then yeah. So some of the common names that they use is like con1, con2, and so on for the convolutional layers, and FC6, sorry, yeah, FC7 and 8 for the fully connected layers. And so this got the second place in the ImageNet recognition challenge, and first in the localization. Localization is like, it's not just classification, but localizing where the object is in the image. So you kind of draw a bounding box around the image, and the training procedure is similar as the last one, and so in this you don't do any local response normalization. So in the AlexNet you had these normalization layers in between. So it turns out that adding or removing those layers doesn't really add to any performance improvement. So they just remove that. And there are two variations of this, which is a 16 and a 19 layer. And 19 layer is only slightly better with more memory. And so use Ensemble for better results. And finally, the FC7 features, that is a fully connected features, can also be generalized in other tasks, like if you're training an image, and then you can just use these FC7 as feature vectors for your other classification tasks. In the sense, you can just put it to an SVM and do some classification if you don't want to like retrain the whole network or something like that. So yeah, so that's it for VGG. And next we'll move on to GoogleNet. So I'll just pass over to my teammate here.
Hi everyone, I'm Karthik. So I'll talk about GoogleNet. In the ImageNet challenge, GoogleNet like competed with VGG the same year, but GoogleNet performed a little better, and GoogleNet had an error rate of just 6.7%, and they emerged as winners there. The major difference that was there was why this GoogleNet was brought up was to make it more computationally efficient. And this was a little deeper, like just 3 layers extra, that's 22 layers. And the advantage was it didn't have any fully connected layers. And they reduced the number of parameters with the help of something called as the inception module, which I'll briefly explain. And because of this, they're able to bring the number of parameters far less than what was there in AlexNet, which was around 60 million. Being an 8-layer network, and this one is a 22-layer network with just 5 million parameters. So I'll just explain what an inception module is. Inception module is something like a network in a network structure. So what they have done is that instead of stacking everything vertically, so they have grouped, they made a local network as in such. So they group in different convolutions. They take an input layer, have a few convolutions happening parallelly, and get out an output layer, and then use this output as the input to the next inception module. And they have done this, and in this case, they have used 9 inception modules for the Google Next structure. So this is a very naive inception module. So if you see that, generally, if you take a layer, so what you do is that you'd have convolutions like 1 cross 1, 3 cross 3, or 5 cross 5, or you do a max pooling or something. So what they have done, that they have done all of this parallelly, and the output, what they'll do is that they'll just concatenate together. So basically making it deeper. So there is a problem with doing all this. So the thing is, since we are concatenating it, it will make the depth quite long, and the number of parameters increases drastically. So I'll just show you the example. So this is like this is the normal an input taken here. For example, it's 28 cross 28 cross 256, and the layers which are used was 1 cross 1 convolution layer with depth of 128, and 128 filters, and 3 cross 3 was 192 filters, 5 cross 5 was 96 filters, and 3 cross 3 max pooling. So what happens is when you calculate, you would notice that this 28 cross 256, when you apply convolution, you'll get 28 cross 128, and 28 cross 192. And similarly, when you are getting this number, which is quite huge, and when you concatenate together, you get a depth of 28 of 672. So that is your layer would be 28 cross 672. So to deal with this problem, what was done is they introduced something called bottleneck layers. Okay, so this calculation would take around 854 million operations. So to handle this, what they did is introduce something called bottleneck layers. So in this bottleneck layers, what they would do is that before applying the convolution, they would apply something called a basic 1 cross 1 convolution to reduce the depth. Basically, they're doing dimensionality reduction here. So by doing this, they are losing some information, but that is being like, in a sense, that compensate for the computational efficiency, basically. So this is your new inception module with a dimensionality reduction. So what you would see is, you would see 1 cross 1 convolution layers applied before your 3 cross 3 and 5 cross 5, and another 1 cross 1 convolution after your max pooling layer. So what happens to your calculation is, basically what you do is that your 28 cross 256 before the 3 cross 3 layer, what would happen is that it reduced to 28 cross 64. So what happens is that here, like overall, when you're applying the same thing across the whole inception module, what happens that the same calculation, which was around 854 million operations, reduces to 358 million operations. That is like less than it's less than half of what you were doing initially. So what happens is, because of this, you are able to calculate your parameters more efficiently. So what then moreover, what if you look at the whole structure, so how the whole structure is, if you see, initially they have 2 conpool layers, and followed by that they have 9 inception layers. In that 9 inception layers, what they have done is that they just don't have one output, but one classifier layer, but they have 2 more auxiliary classifier outputs. The reason being is, so introduction of this auxiliary classifiers allows them to do back propagation, and allows them to add in gradients, because there's a good chance of vanishing gradient when the layer is going deeper. There's a chance that the gradient stops having an impact in the earlier layers. So basically, there is no change in weight, and the point of going for a deeper layer is wasted. So that's where the auxiliary auxiliary classifiers were used. So these basically these auxiliary classifiers are used to inject additional ingredients at lower layers.
So those auxiliary outputs, they're not used for classification.
Actually, they are actually the total loss is calculated as a weighted average of the auxiliary classifiers as well.
Okay, so they use the outputs.
Yeah, they use the output also because their assumption is that intermediate layers also has some information which can be used for the classification purpose.
But they are not used during the inference, right?
Sorry?
During the inference, during testing.
Actually, they're saying that some weighted form is also used.
Oh, I see.
Because in the lecture, what they said is that they're not sure. So I was just reading something, and they said that the intermediate layers are given a weight of 0.3 or something, and they're using it.
So they're using it for testing.
What?
You'd have to use it as testing.
For testing it, but like the major weightage is given to the final layer. But what I see is that the intermediate layers are still used because there could be some information for based on your earlier layers from classification.
But I imagine that the earlier layer will have lower performance. So if you calculate a weightage, then
no, but they give lesser impact for that because their assumption is since it's a deeper layer, there might be some information in the like some information which is available directly or easily you can get it. So those things can be captured in an earlier classifier. Yeah, so the thing is, this layer basically the advantage of this is like computationally it performs far superior to VGG or AlexNet, and it performed like with a 6.7% top error, and it won that year 2014's ImageNet challenge. And then so after this is where we go to really deep layers, and my colleague will.
Hello everyone. My name is Khan. So let me see. Because the ResNet is quite complex, and even I don't get all of the information. So I just try to explain what I understand. So the ResNet is the winner of the visual recognition challenge, and its win completely sweep on all the other classifications because it have the around 152 player, and the loss is around only 3.57%. So let me go to a little bit more. So actually, this is the motivation. So the question is, what happened when we continue to stack deeper layer on the planned convolution network? So in another meaning, for example, when we use the VGG or GoogleNet, what happened if we put more and more layer inside? So to answer this question, they have another graph to compare. So we can see here they have two models, one is around 56 layer and one is 20 layer. So even in the testing, the 20 layer is still performing better than the 56 layer. But when we see back to the training, there's something happened in here because we understand that the more deeper, then it's called overfitting. But the overfitting, it makes the training should be better performance and better accuracy from overfitting. So that means in this case, the more deeper of the network, the causing is not come from the overfitting. Then I come out with the question: if it not come from the overfitting, then what it come from? So my suspecting is only it come from because the vanishing the gradient. That means every time when it go deeper and deeper, the back propagation go inside, then the weight until a time it cannot change anymore. Then it's called vanishing gradient. Then this is causing the problem. Then they come out with the hypothesis is the problem is the optimization problem. So the deeper model is very hard to optimize. So they do to answer this, they do something like they said that at least the deeper model should perform at least better the same with the shallow model. So to using this one, they copy the learning layer from the shallower model, and then they put another additional layer, so that they make sure that with the copying of the learning layer can have the deeper model at least perform the same. So this is the how they do with the architect to make it look a little bit better. So what happened is they put the residual mapping instead of trying to fit underlying mapping. So it's only a little bit complex. So what happened is instead of for the normal neural network, we use the input, we put in two convolution layer and then output. So and then after that it repeat again to use this one input for the next layer. But in this case, instead of this, they plus with the x in the identity with the residual network. So basically, the h of x will equal with the f of x plus the identity, or it's kind of like the hex of x is equal with the residual plus the identity. So for this one, what I'm thinking is whether they to be their point of view when they passing the input to another set of layer, they want to pass the gradients inside. Then it will keep maintain the gradients, and later the deeper the better the result. So what happened is, the fully ResNet architecture look like is first is they stack the residual block. Then every residual block they make around 3x3 convolution layers, and after that they double the number of the filter and downsample the partial using the tribe tool. Something in here, something belong here. Yeah. Then they adding another convolution layer from in the beginning, but they didn't. They won't add the there's no fully connected layer at the end. Only fully connected around 1000 to output the class. So this one I even don't know whether what happened if there's more than 1000 fully connected layer. Like whether they put more than 1000, like 1200 output class, then whether it's fully connected or not. This is also one of my question. And yeah, so this is yeah. For example, in here they said that there are no fully connected layer at the end, so only fully connected layer 1000 to output the classes. So what if it's more than 1000?
No, I think there's 1000 classes.
Yeah.
So it's fully connected.
Yeah.
So I think if you have 1200 classes, then you have fully connected.
Yeah. Something. Yeah.
So what's that?
It's just
1,000 classes.
Yeah.
To be
Yeah. It's also
like 1000 it equates to the number of output classes you have.
Okay.
So if you have like 1200, you have to like retrain with 1200 dimension
200 classes as well.
Fully connected layer. Yeah.
From the network, right? SC1000, can you scroll up a bit?
Yep, sure.
SC1000 is not the last layer.
Yeah, it's just below the softmax.
Below the softmax. Below the softmax.
Okay, so it's not. It is part of the classes, and it should be at the softmax level, right?
No, softmax is kind of like just an activation function. Yeah.
Just converts it to like probabilities and etc.
So yeah, for the totally deep, it is continue to increase around like 45, 50, 100 or 152 layers. So I also that what happened if they put more deeper inside, like more than 152, then whether the performance is better or they have good or not. So because they have some reason that they stop at 152 layers. So
I want to ask, okay, just now I look at the ResNet paper, right?
Yeah.
Just now you mentioned that one of the reasons why they think the deeper networks perform worse is because of the vanishing gradient.
Yeah.
But in the ResNet paper, they stated that it is unlikely to be caused by the vanishing gradient because they say, let me check. They say because of the use of batch norm and the initialization, and they said they also check the gradients, and that the gradients are not actually vanishing. So
it is not vanishing.
it is. They are not. It's in the presentation. Yeah. So yeah. So, but they don't explain why.
Yeah.
So,
yeah. So because if not about overfitting or vanishing gradient, then
it's vanishing was what they suspected. But then I think they did some tests, then they found out. They come to the conclusion that vanishing gradients are unlikely to be the problem, and that the problem is because of the optimization method. I don't know. Then they just thought it's harder to optimize. Yeah, but they don't offer more explanation. Yeah.
Okay. Yeah. Thanks for the new information. Then for another information about the ResNet, they use the bottleneck layer to improve the efficiency. It just look exactly like they copy from the Google Net. Because sometimes it feel like they feel like good, then they copy a layer. So this one maybe we already explained in the Google Net part, so I skip it one. So for training the ResNet in practice, they have fast normalization for after every convolution layer, the Xavier divide to initialization, and plus with the gradients, the HGD and momentum, the learning rate 0.1 divided by 10 when validation error. Mini pass size around 256. Weight DKE 10 times minus 500. No dropout use.
Why didn't they use dropout?
Yeah.
Did they say why didn't they use dropout? Does anyone know?
I only saw in the video that they put that in the paper. They said no dropout use, and there are a guy who implemented this one using TensorFlow, then and Keras, but then it's still no information why they didn't use the dropout. So yeah, this is the experimental result. So it's just the marketing for the ResNet, like 152 layers, actually lower training error and sweep on the other competitions. So that's complexity. You go for it.
So moving on. We see a trend from 2010 to 2015, like how the networks have been trained as shallow and to slightly deeper networks to like very deep networks in 2015. Like 22 to 152 is a huge change. So when in terms of complexity, so the graph in the left is basically showing the top one accuracy of all the networks. So it's like higher the better, and you see how the accuracy has improved steadily, and for the final one is basically Inception V4, which is basically ResNet plus the Inception network together, and that has the highest performance in the slot. And
so what is Inception V4? How do you compose ResNet and Inception together? Did they give it any details?
They haven't. No, they haven't given any. I think they're in the other architectures also that they're going to describe. And the graph in the right is basically the is basically talking about the complexity and the so it's basically accuracy versus the number of operations, and higher the accuracy, and the circle is basically denoting the number of memory, or so it's like bigger is worse. So if you see that the BGG has the most operations and the most memory, and in 2014 GoogleNet won, and if you see the comparison between GoogleNet and BGG, it's a huge difference in the compute in the number of operations for the same accuracy level.
Sorry, what is ENet?
Actually, I'm not sure. So yeah, yeah. So I think they're just comparing a bunch of networks. So yeah, so you can see that GoogleNet is the most efficient one, and AlexNet is also like a smaller compute, but it still has a considerable number of operations and low accuracy. So you can just use this to like quickly compare the different networks, and so for the ResNet, it's like it's like a moderate efficiency depending on the model, and it gives you like very high accuracy. And in terms of the operations, yeah, it's moderate in efficiency. So this one is like comparing the forward pass time and the power consumption. So I guess they're like talking about how it is. I mean the training time, probably like the forward pass time per image versus the batch size. They're just comparing the different networks, and in this case it's like the net power consumption versus the batch size. So yeah. So previously we just saw the famous architectures, like the ones which won the visual recognition challenge, or the ones which has good similar or good performance. So in these networks, these are all like good to know architectures, and mostly they are like working on some improvement in the existing architecture, or something like that. So the network was a paper from 2014. So it's talking about this MLP conv layer, which is basically like a network within a network. This micro network uses these 1x1 fully connected 1x1 conv layers, and the idea is you stack up these NLP conv layers in between different convolution layers, and you try to train the network, and you can kind of think of this network as a inspiration for, I mean, GoogleNet was kind of inspired from this paper, I guess. So yeah, so that's network within network. And in the couple of next papers, we'll be mostly seeing about how to improve the ResNets, and this paper was actually published by the same authors as ResNet, and I mean, like, they're just continuously working on improving the models. So what they're doing here from the original paper is that they're kind of changing the path of propagation for the residual pathway, and they've basically put in these batch norm and ReLU layers in between the convolution layers, and it gives a better performance. So that's like identity mapping in residual networks. And another paper is basically the one which we were talking about in the initial during the ZF network about improving the width of each layer. It's basically like the paper argues that more than the residuals, it is the depth which is more important. So what they're doing is instead of having a very deep network, they're just changing the width of each network. So instead of having having F filters, they're just having this F times K filters, and they show that instead of 152 layers, having a 50 layer wide ResNet can give better results by increasing the width. And they're also telling that increasing the width instead of the depth is also more computationally efficient, where you can do these parallel operations on a wider residual block. Yeah. So the next one is, I think this paper is also from the same original authors as the authors of ResNet. And so what they're trying to do here is, I think these two papers came out around the same time, and I think they are also like thinking in terms of using wider residual networks, but instead of just increasing the width directly, they are kind of doing these parallel pathways, which is similar to the inception module. So using these one cross one conv layers before doing the bigger convolutions, and it's basically the same thing, but instead of using wider filters, they're just using different pathways, and they call it cardinality. Yeah, so that's one. And then for the ResNet, I think the other paper is deep network with stochastic depth. So so one of the issues with training deep networks is the vanishing gradient. So I think what they're trying to tell is when you're like training a ResNet, they randomly drop a subset of layers, and they bypass those layers with the identity function. So if say for example you're dropping these two, so instead of these layers, they'll just bypass it with the identity. So during training time, they're just dropping certain layers, and one after the training, when you're like during test time, they are testing it with the full entire network, something like that.
Like structural dropout. Right? So you're saying you're going to take dropout, but not for individual neurons, but
for whole structures, like whole subsets of the network. Yeah. So so that's one. Yeah. So in this, okay, after this, we are going to talk about like two or three networks which are which are moving away from ResNet. So what they and this one is a recent paper, 2017. So the key argument for the factorial net is that they're telling that residual representations are not necessary, and the key factor is how you transition from a shallow network to the deeper layers. So they've come up with this factorial architecture, which is basically so they have a factorial architecture which allows both shallow and to the final output layer, and then so it looks something like this, and to the previous paper that we saw, where they drop out certain subpaths. So when you're training, they just drop certain layers, and after the training, they just use the full network during the test time. So yeah, that's the idea behind it.
So do are the filters shared across these different convolution units, or is it like each level will be the same?
I'm sorry, can you?
Like like the in the diagram, each like the pink blocks, they are convolution, right?
The pink blocks are convolution.
Yeah, and then do they each have a unique set of filters, or do they share the filters?
Yeah, I think it's unique.
Across, like,
yeah, I think it's all different. I think it's all unique filters.
The only thing that seems to be preserved is the join layer. Right?
Yeah, I think it's like during the joining layer, they kind of, I don't know if it's like a concatenation or.
It says join.
So,
yeah, I mean, if it's not join, it would be exactly the same as ResNet, right?
Yeah, so yeah. I'm not really sure what's happening at the join layer.
I think probably concatenation.
Yeah. So maybe it's just that the ResNet doesn't have a direct connection from the shallow to deep. So over here, it's more like factoral. You have multiple connections where it goes from direct to like after multiple connections, I guess. So
but are those they are fully connected layers? Are they fully connected? FC means fully connected.
FC is FC is. FC. Oh wait, I don't.
It's just function.
I think it's function.
This F is like function, not fully connected.
Yeah, I think it's just some function.
I don't think it's
fully connected. Yeah, it doesn't make any sense. Yeah, it's just some function. Yeah. Yeah. So yeah. So another paper which is moving from ResNet is a densely connected convolutional network. So the intuition behind a densely connected convolutional network is that so you have a network where each and every layer is connected to every other layer in a feed forward fashion. So it's basically like it elevates the vanishing gradient. It strengthens feature propagation, and it encourages feature reuse. So basically, I think the idea behind this is you have a bunch of concatenation after the conv layers. So it's like it's I think it's similar to I think it's similar to like GoogleNet in terms of the concatenation. You have the input, and then after you do the convolution, you concatenate the input with the convoluted image before you send it off to the next convolution. So like even at the deeper layers, you're kind of using all the features, all the lower and mid-level features, I think. So
general question: how do you go about designing one of these nets? Arbitrary, it can't be, right?
But I don't know. I don't think there are any. I mean, I don't think they give a explanation to why they are doing this. Probably they talk about. Actually, I haven't read the paper, so I'm not sure.
No,
sorry. Yeah.
Because, how do you go about mathematically proving or simulating a 152 layer net? So.
Well, I think the answer to that is you just try. I don't think because there's enough forward progress being made that the error rates are falling so fast that the theory is not following the practical, So people are just,
trying
shooting their guns everywhere in hoping of hitting the target function better, right? So, I mean, a lot of the different things that you're exploring in this section of the lecture is basically people just, they've got lots of computation, so they're just trying different things, right? So part of it is they're trying to reuse the output at each layer to help, and you see the fractal net and this densely connected convolution network. So basically going after the same thing, saying that intermediate output is somehow useful, and we saw that even in the Google Net, right, where they said you're going to plug in intermediate outputs and then use that to back propagate and help you vanishing gradient. And then the other ones are, okay, if I'm not going to attack accuracy, I'm going to attack efficiency, right? So if I can do the training more efficiently, maybe I can put it to multiple domains and multiple data sets faster.
Yeah.
There's also people saying that you can use reinforcement learning to learn the structure. Like this is the new 2017 IPML paper. Like they use reinforcement learning to learn the
Google Brain, right?
Sorry?
So I think it's a Google Brain paper.
Yeah. To learn the structure and the accuracy is like to state of the art.
But how does it really work? Like, does the algorithm try different combinations?
Yeah, you can read the paper at that time. Like they use the controller and one controller. I haven't read the paper.
But I imagine it's a lot slower than.
Slower,
right? Is it slower than manually?
Like a little bit slower, but accuracy is the same. You can.
It's not only the network, there are other parameters for hyperparameters for the optimization function, everything.
But there has to be a limit. So basically, I guess this is a way of tweaking some parameters, like number of layers, number of filters.
Even the structure, topology.
So it's gonna tell you.
It looks really weird if you look at the networks that the system discovers. It's nothing that humans could have ever come up with.
So it's come up with the architecture itself, is it?
The connection.
Yeah, the connections.
Is it following the same intuition?
Yeah, it's the same intuition, yes.
Like the neural network has a natural. The network itself has a natural.
Right, but the what genetic algorithm optimize for is very different from what reinforcement is.
Do you know what
It can be more focused.
I
don't know, but I think it's still image.
I see.
You can open the paper. Yeah.
Okay, just finish this and it's probably okay. So so the last paper that they're talking about here is SqueezeNet, which is basically moving towards more efficient networks. So basically what they're trying to tell here is you can get AlexNet level accuracy with 50 times lesser parameters and less than a 0.5 MB model size. So basically they have these FIRE modules which consist of squeeze layers, which are like 1x1 filters, and then followed by an expand layer, which is like a 1x1 and 3x3 convolution filters. So basically using these modules, they're getting AlexNet level accuracy with 50 times lesser parameters, and they can compress the model to 510 times smaller than the AlexNet, which is like lesser than 0.5 MB. So it's like really small models.
What is it called FIRE? What is FIRE?
Just maybe a cool name, probably. But I guess, or maybe there is a acronym for or something else.
Okay.
Yeah. Right. So in summary, we looked at some famous models like AlexNet, BGG, GoogleNet, and ResNet, and we also saw other networks. Yeah. So So in summary, BGG, GoogleNet, and ResNets are all widely used, and these are all available in Model Juice. And currently, ResNet gives the best result. And then we saw a trend which moves towards extremely deep networks. And at the same time, there is also like research which is going on around skipping layers or connections, and improving the gradient flow between the shallow and deep layers of the network. And there is also a trend which examines the necessity of depth versus width, which we saw in the residual connections. Like, do we need residual connections or not? Yeah, so that's basically.
Questions? Any question you want to add?
There was some discussion of vanishing gradient problem here as well, right? Which network did it start happening? From ResNet?
From ResNet.
Does ResNet actually address the problem? Is it a solution to the vanishing gradient problem? I missed that.
No, because I suspect that the vanishing gradient is causing making in the ResNet. But then he said that in the paper, they said that this is make the very small. It not affect the ResNet.
So what I mean is, in the ResNet paper, initially they suspect that it was a vanishing gradient.
What is the name of the paper?
Problem, but they do like some experiment. I think they check the gradient to see that they are not actually vanishing. So they basically rule out that deeper network cause vanishing network problem, and that the problem is caused mainly because deeper network are just harder to optimize. Not necessarily because of vanishing gradient. Yeah, maybe you have to try more combinations to get the right one. Yeah.
The vanishing gradient problem does not come until you have recurrent nets, right?
That one I don't know.
Yeah, that's well known. Recurrent nets you have vanishing gradient. So in columns there is no gradient problem.
I'm trying to find a real learning paper, right?
Because the authors specifically say this, the use of batch now alleviates vanishing gradient.
This one is the one you were talking about.
I think vanishing gradient is causing the normal condition.
Oh,
like
right.
When you put more and more layers, it will consume. But no.
Yeah, I think
this is the one you were talking about.
Yeah, it will probably happen. But with batch now, it's harder to happen, I guess. Yeah.
Yeah, so I guess this is the paper for the.
Yeah, come down and look at the figure. No, further down. Is that the machine discovered figure?
No, no.
Oh, sorry. Hey, what? Yeah, so which is the.
Not there in the paper.
The figures in the blog post. Yeah, in the blog post, they show one picture that's like all over the place. I think that's the one that we do.
Yeah, they showed it in their slides in their presentation, the TensorFlow talk at Google.
Because using machine learning to store neural network architecture.
Oh.
That reinforcement learning, is it a deep reinforcement learning or not? Is that what
what is the block?
Using machine learning to explore neural network architecture.
Is that deep reinforcement learning as well?
This one?
Oh, let's go down.
Okay, so I think that's the first one.
That's
the machine discovered architecture.
This is the one.
Yeah, that one was GoogleNet.
Oh, that one is Google.
Yeah. Oh, this is the one.
Yeah, it doesn't look like them.
Yeah.
Huh.
Even Google doesn't look like it. at least in NLP, you don't see this kind of big stacks of networks.
But this is not really a kind of a it's more like a traditional NLP kind of. It's not for image recognition, right?
What are the tasks they do? So there is C part 10, I see.
So they say they're on this paragraph. So what kind of neural network does it use? So this is a RNN, a recurrent network architecture for natural language. This is pen tree data set.
Even this one.
That one, yeah.
Oh,
in the previous paragraph, where we're on the laptop, it says so what kind of neural network. So this is an RNN which we'll study next week that they created using their reinforcement learning. If you guys took any type of like genetic algorithm or reinforcement learning stuff, that's what this diagram would have looked like maybe in the 1980s, but just redone for having those that represent deep neural nets now.
So what is the algorithm deep reinforcement learning as well, or is it a normal machine learning?
I think, I'm not sure, I didn't read the paper, but it seems like it's basically some type of genetic algorithm or reinforcement. It doesn't have to be deep.
Yeah.
Right? You're just taking the fitness of several different hypotheses, comparing it, and whichever one is better, you keep that part of the network.
The problem with genetic algorithms, it's very, the fitness function is the key there. You still, that's, just like you have parameters.
Fitness function. Your fitness function is the loss function in your error, right?
Oh, okay.
Using that to do the back propagation, then you have your fitness function, and they have some way of like permuting the nodes in your network, either by proposing new layers or crossing new layers or adding layers together, right? And so it can come up with whatever, like a Christmas decoration version of a network as it likes.
What is the size of the pantry bank data set?
Very small.
Very small. Yeah,
very small. About millions of words only. Words, not even pixels. So yeah, very small.
So is this kind of algorithm applicable for real world tasks now, or this is more like for toy problems? Like
I would guess they did it. Well, it wasn't a toy problems in the 90s. Now it's a toy problem.
Oh, is it 90s?
No, I mean the data set is a real data set that's used to train, any type of summarization and natural language processing.
Oh, I see.
Yeah, like Mutu's data set is based off of the entry bank.
The reason you do everything on Petri Bank is that so they took a section of Wall Street Journal corpus and then they annotated it for basically part of speech tags. So that's how it started. And then they define their own set of part of speech tags. I mean, that is the state of that was shown on that, and then that became the baseline, kind of like an image line. Okay, and then on top of this, they built discourse tree bank, which are higher level structures on top of sentences. Okay, so and then various
topic,
not topic, discourse stacks. So which means that different clauses and different sentences could be related by certain relations. For example, I am here because there is a class from 6 to 8. So because discourse relations, it's implying causality of these two structures. They're higher level structures. Right? So annotating these things is a very difficult task. So if you have a lower level annotated corpus annotated on top of it, it adds value to the same corpus. Right? So I can now use the part of speech, annotated part of speech, as well as the discourse tags together in my algorithm. Yeah, but then that's really small corpus compared to. I mean, there are some replacements that have been proposed. For example, New York Times corpus these days that have been used for a lot of information extraction tasks. There is also Wikipedia dumps and Freebase. That is very popular information extraction task. Information extraction in the sense you extract entities and extract relations between those entities and construct a big knowledge graph. Right? That Google is currently using to output your. So when you Google for something, it comes up with like factual answers, right? So those are just extracted directly from those knowledge graphs.
So we can talk about it more next week.
Yep.
That's more like the
recurrent
lecture. Yeah, but to answer Mutu's earlier question, this is actually done just using standard reinforcement learning, not deep neural net. Deep reinforcement learning. If you read the rainfall. Other questions, comments? Nothing? Okay, then let's thank our presenters for today. So next week, who are the presenters for next week? I see you guys talking on Slack. That's good. Anyone here? Not here, okay, but still talking on Slack at the same time. That's great. Okay, one person. Okay, two. Okay. So we hear from you guys on recurrent neural networks next time. Just a note, we need all the project proposals in this week from external parties so that we can allocate enough spaces for you during the poster session. Again, I would suggest for all projects that you try at least something that's a baseline system, meaning that you just replicate somebody else's work using, a machine learning library like PyTorch. I guess Piano is on its last legs. But then after that, if you have time and you wish to do it, then propose the other, carry out the other parts of your project. Okay. Great. So just keep in mind, week 10 we'll have a guest lecture after the main lecture from the folks at Resense. They're going to come down and talk about how they're using DNN in their image product recognition work. And then likely either week 11 or week 12, I'm going to propose that after class we have a social, just so that we can talk informally again, because that seems to be is not just having a lecture, but forming a network around these things, especially if you're from industry, you may hear about AI.SG, all the stuff around there. And many times those types of initiatives have funding from the government, but they also require some type of collaboration. So right now you have lots of students next to you, and students, you have a lot of industry collaborators next to you. So I hope that we can get at least 1 or 2 proposals for 100 AI 100 projects out of this group. Okay, so I'll talk more about that on Slack once I get my act together. Okay, thank you. AI.SG is providing funding. Do you guys know about that? You want me to go over that? AI.SG?
I get a lot of money.
Can some problems about the replication. My name is
Yeah, you sent me an
email,
right?
Because I'm the customer for both week 10 and week 11.
Yeah,
So,
I need to fix that for you.
okay,
Yeah.
so still in India, I will do my presentation in week 10.
It's up to you because we have enough people for both week 10 and week 11. So you can choose whichever one is more fitting with your schedule, and you can decide for that. So if you guys are interested, there's this 100 experiments part of AI.SG. So the idea is they want to take people who understand a bit of deep learning and try to transition them to do something in industry. So you want to reach some type of minimal viable product in 6 to 18 months. So whatever project you're doing is already like 1 month. So you can consider that. And then you can tap on some students here who might be interested. Just shout out on Slack and say, hey, do you guys want to work together? We can go get some funding. We can try to put something together and propose a project. Of course, it's not limited to people in NUS. This is all SG wide. So if you happen to have students that you know at SMU or NTU or even SUSS, then you can ask them for that. Okay. So this just went out a couple of days ago, but this is I think quite useful if you want to get funding for it. Maybe if nothing else, you can buy yourself a nice TPU, install it in your machine. Yeah.
No, they're giving you money, so you can use it to go buy manpower or compute power. I mean, right now it seems like compute power would be
I don't
useful.
think TPUs are on sale.
No, yeah, but you can rent them from
Yeah, you
Google,
can
right?
rent them.
They're a part of the Google Cloud infrastructure, yeah. Or you can buy some NVIDIA products and help fund them, yeah.